Hello everyone, welcome to the second lecture. It is actually a continuation of lecture 1. In lecture 1 we discussed about the introduction to data structures, the definition of data structures, its classification, what linear data structures are and its example in detail. We looked at some of the nonlinear data structures and then we concluded with one real world example of the appropriate data structure to implement a contact list. In this lecture, first we will see what are all the possible operations that could be performed on data structures. You see on screen various operations like creation, deletion, searching, selection, sorting, merging operation, traversal operation, insertion and updation. Let us see one example for each of these operations. For instance, let us consider employee data set. For with respect to creation, you know very well, in order to create an employee data set, you will be using any of the data structures, say array or linked list. So, we in terms of creation, we may have to use either static or dynamic memory allocation if we make use of arrays or linked list respectively. So, creation corresponds to memory allocation for each of these maybe we use arrays or linked list for its implementation purposes. And when it comes to insertion, let us consider that we add a new employee to the already existing employee data set. That becomes inserting a new item into the existing data structure, be it list or arrays. And updation is modifying one of the fields of the data item in the list, that could be updation. Traversal in the sense we navigate from start till end in the existing data structure, if it is an array or a list, to look for particular or to display all the employee records that are part of that employee data set. Search operation is like we are given with the key or to search for a particular employee in the employee data set, and you could use you could look for a matching key in that employee data set to provide an answer as matching key for the particular employee. And you may have even selection operation done. So, with selection we mean that we look for some particular value or particular record in that employee data set to be selected as a result. And merging operation in that sense, for instance, we may have different departments employee information in separate lists, and if you want to have a combined list, then we will go with merge operation. You could merge two lists into one, and then you could go ahead with sorting operation, which actually provides or orders all the elements in that data structure in either ascending or descending order. And deletion operation in that sense, if suppose an employee leaves his job, then we may be removing his records from the data set. So, in that case we will go ahead with deletion operation. So, these are the possible operations we will be using on the different data structures, be it linear or non-linear, which we discussed earlier. The next important topic which we are entering into is abstract data type. So, far we have seen separately the different data structures, and we have also studied what are all the operations that could be done on those data structures. So, the definition for abstract data type is, it is nothing but a set of data along with the operations that can be performed on that data. Together we call it as an abstract data type. So, the fact behind abstract data type is that we put together data and its associated operation, while we hide or separate out the implementation aspects. Consider the same employee example which we discussed earlier. I was mentioning that you can have an employee data set being implemented using either arrays or linked list. Let us imagine that first of all we have used arrays for implementation. If at later point of time, if I think of adding one more field to the already existing employee item, or if I want to move from array to linked list, then I may have to bring in lot of changes in each of the functionalities or the operations. So, implementation wise it is going to bring in a lot of changes. That is why we talk of abstract data type. We always say that data and the associated permissible operations be put together, while implementation aspect has to be separated out. So, in this course we will be learning about many data structures, and each of those data structures we will be saying as list ADT or array ADT. So, by which we mean the data structure plus its operations. Say for example, if we say array ADT, it means arrays plus what are all the operations that are permissible on arrays, like insertion, deletion, search, modification of an element, or even deleting an element from an array. So, we say this as an abstract ADT in abstract data type, or ADT in short, which is array ADT. Now, we look at some of the importance of data structures. I have listed out some 7 to 8 importance of data structures. Let us see each one of them in detail. The first is efficiency in data management. So, here by efficiency we mean we want the data structure to provide or facilitate faster access times. Say for instance, if suppose I organize my data in the form of an array, or if I organize my data in the form of hash data structures, we can say that I have arranged the data in some better way, and that facilitates a faster access. But performance wise, we know very well that hashing is somehow better and faster when compared to implementation using arrays. And also, by organizing the data efficiently, we actually optimize the storage. You know, memory is also an important resource, and we should never think of wasting memory. And organizing data using any of the data structures actually help in improving the efficiency with respect to data management. The second importance is performance optimization. So, the performance of algorithm actually depends on the underlying data structure being used. So here what I would like to stress upon is the algorithms should carefully pick upon the right data structures in order to enhance or in order to have a better performance, or to have an optimized solution. The algorithm should have or should make a right choice of data structures. And scalability and flexibility, in that sense data structures provides us with lot of flexibility in accessing the data, but we should also think upon its scalability. What if the size of data gets increased? So, if we deal with large data sets, then we need to be careful about the data structure we use. For instance, B trees and B plus trees could be used when we go for indexing a huge data set. And the fourth importance of data structures is with respect to foundations for algorithms. You know, data structures is the building block upon which algorithms are actually built upon. So, for instance, we will be learning about many of the graph algorithms, and those graph algorithms actually use graph data structures underneath. So, we say that data structures are actually the foundation upon which algorithms are actually developed. And the fifth advantage or importance of data structures is with respect to system design and development. So, we have been discussing, we might have learnt about different systems. Say for instance, you might have learnt about databases, where for indexing purposes we will be using different data structures. For instance, hashing we may be using, and if it is larger data sets we may be using B trees. And you know, our operating systems also make use of different data structures. For instance, it makes use of queues for scheduling purposes. It can be even process scheduling or task scheduling. And you know, in printers also we will be using queues for job scheduling purposes. And CPU also uses different data structures for different purposes. So, underneath all these systems we have data structures built into it, and data structures are even part of many of the real world applications which we come across. Say for instance, the best example I could tell you is with respect to GPS systems, we use graphs. So, in a map, different cities are plotted as vertices, and in order to find the shortest distance between two places, we will be using some graph or shortest path distance algorithms, etc. And in case of social media, we will be using again graph data structures to picturize or visualize relationship between different users. So, thereby data structures play a vital role in many of the real world applications. And the last importance is it helps in enhancing the problem solving skills. So, if you want to propose a solution, then you may have to look upon the right data structures and right algorithm to solve that problem, and you could bring in innovations with the help of the right choice of algorithm along with appropriate data structures. Having seen some of the data structures, its operations and importance, now we slowly move on to the next concept of algorithms. So, algorithm, you know, it is a set of steps to solve a problem, and those steps should be finite and it should yield a solution to the problem on hand. So, in order to solve some problem using a computer, you may have to adopt an algorithm which actually defines the set of steps to solve the problem. And here in this slide, you see an example of an algorithm to decide upon whether to buy a car or not. And in that case, the algorithm actually defines us the set of steps to solve that problem of buying a car or not. And it even looks at the steps like is the public transport appropriate for reaching out to a particular place, and will the user be making frequent travels outside. So, these are all the considerations which that algorithm actually makes, and each one of these actually become the step in an algorithm, and depending upon the choice the user makes at every step, there is a decision making there happening, and ultimately the algorithm ends up with saying whether the user should buy a car or not. So, in short, given a problem, you could decompose the problem, you could think of a solution first, and that solution can then be visualized as a set of steps. It will ultimately end up with the solution to the given problem. These are some of the characteristics of an algorithm. One is, any algorithm should have a well defined input and a well defined output. So, given a problem, as a developer or a programmer, you should do a logical thinking how to arrive at solution for the given problem. And after arriving at the solution, after thinking of a way to solve the problem, you should think upon what could be the input and what should be the output. So, every algorithm is supposed to have a well defined input and a well defined output. Apart from that, an algorithm is supposed to have certain other characteristics like definiteness, finiteness, effectiveness and language independence. Definite in that sense, every step in that algorithm should be definite and it should be unambiguous, and it should be easily interpretable and achievable, and only then it will be considered as a valid step in an algorithm. And an algorithm, as you know, by definition, it contains a set of steps to solve a problem, and the number of steps that the user should make to solve a problem should be finite, right. Every algorithm should be expressed in minimal amount of steps to solve a problem. In that sense, we say that every algorithm should be finite. And effective in that sense, whatever step we adopt in an algorithm, it should be an optimal one. That is what we mean as it should be effective in terms. There could be many ways to solve a problem, but whatever steps we adopt to solve a problem should be the best out of it. And in that sense, we say that every step in an algorithm should be effective. And the last characteristic which is expected out of an algorithm is language independence. We cannot develop an algorithm having in mind some programming language. So, an algorithm should be general in nature and it should be irrespective of the programming languages we have. So, given a problem, it should have well defined input, output, it should be finite, it should be definite, it should be effective, and it should be language independent. Now, let us see some of the factors of an algorithm. One is modularity. So, whenever we are given with a problem, the first step we do is we try to decompose the problem into sub-problems or modules. So, modularity is one of the important aspects which is expected out of an algorithm. Only if we break down the problem into several modules, then it will be easy for the developer to analyze it further. So, module wise the developer will be analyzing what input should be given to every module, what should be the expected output from every module. So, from when we think of designing, modularity is much helpful. At the same time, when we think of debugging the module, there also modularity feature helps a lot. So, you can test with some random input and we can check whether the desired output is expected from the particular module, and that is one of the aspects of modularity. And the second aspect is correctness. So, if at all we have to ensure the correctness of every module or the algorithm, then as I said, modularity helps in ensuring correctness. And maintainability in that sense, initially you may come up with one version of that algorithm, and later upon if you want to add up new steps to that algorithm, then it should be done, it should be possible with by making minimal changes to the existing algorithm. That is what we mean as maintainability. And functionality in that sense, every module which you have in your algorithm should have some well defined functionality. If at all you think of adding some new functionality, then the algorithm should support that. We can to bring in more and more functionalities to the existing algorithm with minimal changes. The fifth factor expected out of algorithm is user friendliness. So, by in general, by looking upon an algorithm, any user should be able to visualize what are all the steps he should make in order to solve that particular problem. And robustness in that sense, given any problem, the algorithm should be able to handle all possible situations. And extensibility, the algorithm should have it should have the provisions to extend it well with different conditions and constraints and to different functionalities later in point of time. And as such, the algorithm is expected to be as simple as possible while solving a problem and to come up with the right solution for the problem. So, these are all some of the factors usually expected from an algorithm. Now, we move on to what are all the algorithmic approaches available with respect to problem solving. Of course, I have been telling you different kinds of algorithms, and when we look at problem solving and when we propose a solution or an algorithm for bringing in a solution to that problem, there could be multiple approaches and your algorithm may be fitting into any of these approaches. We have certain standard approaches and the algorithm which you develop may be falling under each of these approaches. The first approach is brute force algorithm. By brute force we mean we actually make an extensive search. So, given a problem, the algorithm actually tries to make an extensive search in order to bring a solution to that problem. Say for instance, let us consider we have a password and you know for sure the password is of 3 bits. So, in that case if the password is going to be numericals and all the 3 bits are going to be 3 numbers, then if you have forgotten the password, then what you could make is you could try all possible combinations of 3 digits. So, you could try from something like 101 to 999 in order to come up with the solution for this case. So, this is what we mean as brute force actually. We try to make an exhaustive search to find a possible solution to that problem. And brute force algorithm could be of 2 types. It could be optimizing or it could be sacrificing. So, optimizing algorithm in that sense, as I said, we make an extensive search and try to come up with as many solutions as possible first, and then as a result we will be projecting out one best solution from the available possible solutions. And sacrificing in that sense, if we arrive at one solution to that problem, we will stop there. That is what we mean as sacrificing category. The next class of algorithmic approach is greedy algorithm. The name itself tells it is greedy. So, the algorithm actually looks for optimal solution. At every iteration, the algorithm proceeds in finding an optimal solution for the problem. So, in short, the difference of brute force and greedy is that in a greedy algorithm, we do not stop with getting one solution for that problem. We always try to make some optimal steps in successive iterations in an attempt to find the best solution or the optimal solution for that problem. So, that is the principle behind greedy algorithms. And backtracking algorithms are ones in which we apply recursion. We actually eliminate solutions that does not fit to constraints. We may be having some constraints in that problem, and if the solution we come up with does not match to the constraints, then we think of eliminating that solution and still make an attempt recursively to find some best solution. And then we may be having some algorithms that fall under the category of divide and conquer. So, divide and conquer in that sense, given a problem, the problem will be decomposed into simpler problems or sub problems, and we will be finding the solution for the sub problems first, and finally we will be merging the results of all the sub problems to propose the solution for the bigger problem or the entire problem. So, that is the concept behind divide and conquer algorithm. Then we have another class of algorithm which we call it as dynamic programming. The principle behind dynamic programming is we will be dividing a problem into several sub problems, and then we try to find the optimal solution for sub problems. So, we do not stop there. When we find an optimal solution for any of the sub problems, we actually preserve the results for further use. We call this step as memorization. This is very crucial or important with respect to dynamic programming. After memorizing step, what we do is, if we come across the same sub problem further while solving the problem, instead of recomputing the sub problem, we will be using the results which we have computed earlier. So, thereby the advantage of dynamic programming is that for sub problems we do not try to solve it independently multiple times. Rather, if we have a solution for any of the optimal solution for any of the sub problems, we will be storing it or preserving it and using it later at point of time. Thereby we reduce the computational complexity. And the last class of algorithmic approach is randomized. Randomized algorithms, the name itself says, given an input, it will be giving us a random output. So far we have been talking about different algorithms which are all deterministic in nature. So, we call them as deterministic algorithms. So, deterministic algorithms are ones in which when we give an input, the algorithm will guide you through set of steps and we know an expected output. Whereas, in case of randomized algorithms, to the input some random component gets added up, and as a result the output of that algorithm will also be random in nature. So, as such, when you talk of algorithms or when you develop a new algorithm, your algorithm will ultimately fall under any of these approaches like brute force, greedy, recursive, backtracking, dynamic, randomized or divide and conquer approaches. Having seen the various algorithmic approaches, now we will see how to make an analysis on an algorithm and how to make an assumption or assertion on its complexity. When we talk of algorithm analysis, analysis could be of two types. One is prior analysis and another one is posterior analysis. So, prior analysis is some sort of theoretical analysis which we do before developing a complete algorithm. So, it could be, as an example I could tell you, for instance, before executing or implementing an algorithm, I think of the environment in which this algorithm will be put into execution. I could even suggest processor speed as one of the examples. So, whatever analysis we make on an algorithm before its implementation, we call it as prior analysis. The next analysis which you could make is posterior analysis. So, it is also called as practical analysis of an algorithm. So, practical analysis usually happens after implementing that algorithm. So, already I mentioned your algorithm is built on top of any of the data structures, and after you implement an algorithm using any of the data structures, we usually make a posterior analysis to tell of the complexity of that algorithm. So, we usually express complexity as in two aspects. One is space complexity and another one is time complexity. By space complexity, we mean the amount of storage space the algorithm demands when it is put into implementation. So, by demand I mean the amount of storage it expects for its input, the amount of storage it involves as a part of the program implementing the algorithm, and additional amount of space which the algorithm may demand at runtime. So, all of these should be taken into consideration when we measure the space complexity. And usually for expressing this space complexity, we will be using the notation called as big O notation. So, we usually express the storage requirements of an algorithm as a big O notation. And the next aspect of complexity is time complexity. So, we implement an algorithm and we put it into running, and we measure the time taken by the algorithm from its start till end. That is what we call as time complexity. So, in practice we actually measure the number of computational steps the algorithm makes in order to propose that solution. That is what we mean as time complexity, and time complexity is also expressed in terms of the big O notation. So, your algorithm may have complexity in the order of n, or it may have take a constant time or order of n square. So, here n actually refers to the number of steps the algorithm actually makes. So, while we think of developing a new algorithm, it is in practice we may have to analyze its complexity, and we do not do much of prior analysis, but we have to make posterior analysis and express the complexity of the algorithm in terms of space complexity and in terms of time complexity. To summarize what we have seen so far, so in the first lecture we initially studied the definition to data structures. So, the first definition which we learnt was data structures provides us a way of organizing data. The purpose of organizing data is to later retrieve data in an efficient manner or to store data in an efficient manner. So, we are always bothered about the memory requirements. We want memory to be utilized as minimum as possible, and data structures provide us a way to have conserved use of memory and to retrieve data in an efficient manner. And then we discussed about some of the classification of data structures. We classify data structures into primitive and non-primitive. In primitive data structures, I mentioned it is the built-in one that comes with any program. Ultimately, you may be using any of the programming languages to implement your program or to develop your program, and that programming language by default will have support for the some of the data types, and those data types form primitive data structures. And the speciality of primitive data structures is that such data structures can be very well handled by machine language instructions. The other class of data structures are non-primitive data structures, available data structures. So, non-primitive data structures are data structures that are actually derived from existing data structures, and best examples for non-primitive data structures include arrays, structures, etc. And linear data structure is one in which the elements in the data structure are organized in a linear or sequential manner. So, the elements will be arranged in such a fashion that every element will have a preceding element and a following element. So, if the elements are arranged in such a fashion, we call it as linear data structure. Then we discussed about nonlinear data structure. Nonlinear data structures are one in which the elements are organized in a hierarchical fashion. The best examples for nonlinear data structures include trees and graphs. We also learnt various linear data structures like arrays, linked list, stacks and queues. And we discussed about the important differences between each of those linear data structures. You know, array is one in which the elements are all stored in consecutive memory locations, thereby usage of arrays is very easy, implementation is easy. But the only drawback with arrays is that if suppose we think of extending the size of the array, it is not possible because array is an example for static data structure. Static data structure is one in which memory is reserved at compile time, and later upon we cannot either increase the size or decrease the size. And linked list solves the problems which we encounter with arrays. In case of linked list, we allocate memory depending upon the requirement, and that too in runtime. And so, with the linked list we saw different variants like singly linked list, doubly linked list and circular linked list. And we studied about stacks and queues, and stack is called as a LIFO list and queue is called as a first in first out list, and we saw the difference of it. And we discussed upon the basic operations on data structures like traversal, searching, insertion, deletion, merging, creation, modification, etc. Then we discussed upon the concept of abstract data type, where I mentioned that we use data structures and its operations together and hide the implementation aspects. So, abstract data type facilitates a way by integrating data and its associated operations while separating out the implementation aspects. Then we discussed about algorithm, its definition. So, it says that algorithm is a step by step procedure to solve a problem, and algorithm can be of different may adopt different approaches, like it could be brute force, randomized, it could be divide and conquer, or it could be branch and bound. There are different algorithmic approaches, and you could develop algorithms following any of those approaches. And at the end we will be analyzing the algorithms at two levels. One, we could do a prior analysis or we could do a posterior analysis. And when we measure the complexity of the algorithm, we express algorithm's complexity in terms of time and space, and both of them are expressed as big O notations. So, in order to test your understanding of what we have learned so far, I have given some 6 questions. Number 1, what is a data structure? So, from the available choices, you know, data structures is a way to store and organize data. And then the second question is, what are the disadvantages of arrays? So, I have given some 4 options. One is index value of an array can be negative, elements are sequentially accessed, data structures like queue or stack cannot be implemented, and there are chances of wastage of memory space, and of course, the disadvantage is wastage of memory space, option 4. And the third question is, if the elements of the data structure form a sequence of list, then it is called as linear data structure. The fourth question is, which among the following is a non-primitive data type? You know, primitive is what comes with your program or the programming language. So, here the difference is, integers, characters and doubles are all default data types available in programming language. So, the answer for this question is array. And the fifth question is, which data structure can be used for implementing recursion? Ultimately, you know, stack is the data structure which we use for recursion. And the sixth question is, which of the following statements about stack data structure is incorrect? So, here top of stack always contains the new node, that is true because you know it is a LIFO list. Stack is a FIFO data structure, which is false, you know very well. Queue is an FIFO data structure. So, the answer for this question is option B. So, these are some of the references.